Good day once again, students. We are going to continue with our mass spectrometry. We have looked at the mass spectrometer, and we have reached a point where the isotopes or the molecule is the atom or the isotopes are supposed to be discovered here, so detected here. So how do we see the detection? We see it in form of what we call mass spectrum. Mass spectrum, as we said in our last lesson. So this is mass spectrum for molecular atomic mass, relative atomic mass. For this substance now, we always have for the relative atomic mass here, whether it is atom, relative atomic mass, or relative molecular mass, we always have the relative abundance or percentage abundant. This, you're already used to this. When you say relative abundance, it may be percentage, it may be anything. And when you say percentage abundance, it has to be 100%. You are considering only 100 of it. Okay, either 100 atoms or 100 molecules. Now, this is percentage abundance. We are considering 100. Out of 100, how many of these 100 has a mass over charge ratio of 35? Mass over charge ratio of 35, about 75 of it. About 75 of them. About 75% has a mass, you read it from there. About 75 has a charge to mass ratio of 35. Charge to mass ratio of 35 there, and about 37, about 25% of it has a mass to charge ratio of 37. A mass to charge ratio of 37. So about 25% of the chlorine atom coming from the vaporizer, passing through the bombardment chamber where ionization took place, going through the electric field where acceleration took place, going into the magnetic field where they separated into two, and these detected, and this is the mass spectrum. This mass spectrum is showing us that only two isotopes we have for that element. Now, mass over charge. These represent the masses of this isotope. An isotope with mass 35, this is for chlorine actually. Chlorine isotope 35 has percentage 75% of them, and chlorine isotope 37, 25% of them. Why are we calling mass the same thing as mass over charge? Because the charge is 1 plus 1. The charge of these atoms is plus 1 plus 1 plus 1. So one electron is knocked off, it becomes positively charged, and it is dragged by the accelerator, by the electric field. So one electron is knocked off, so it is positive 1. The charge is 1. Mass divided by 1 is mass. So that's why the same thing, mass to charge ratio is the same thing as the value of the mass. So from here now, you know how we calculate the average atomic mass now, which you know as we have done it before. So we say the average this time around from what we have seen will be equal to whatever you have here multiply by whatever you have down here. This 35, and whatever you have here multiply by whatever you have here 37. The answer to this, you divide it by this plus this plus this. That means just the way we used to calculate before, but this time around you get the abundance from the graph, from the spectrum. So we have 75 multiplied by 35 plus 25 multiplied by 37, and the total divided by the total. What is the total now? We look at the abundances. The abundance here 75 and here 25. 75 plus 25 making 100%. So we write the 100 here as usual. As usual, you understand how to do this. Then at the end of the day, you get the mass, average mass of chlorine. Average mass of chlorine. So, which we have done before. We have done this calculation before. I've given you about 6 calculation or 5 or 6 calculation, and we have solved it. We have the video to that, and you have watched the video. Now, this is how you got those percentages. This is how those percentages came about. The next thing we're going to talk about now is sometimes if that particular element is diatomic, like chlorine is diatomic. Chlorine is diatomic. So chlorine being diatomic means chlorine bonded to another chlorine, one chlorine bonded to another chlorine. This chlorine may be chlorine 35 and this chlorine 35. It may bond to 2 chlorine may bond, and this may be 37 and this 37. And another chlorine may bind. It may be chlorine 37 and chlorine 35. These are the possibilities we have. These are the 3 possibilities we have of the molecules of chlorine. Now, what if during ionization, because the molecule is also an entity, the molecule is also a unit, what if during ionization we do not have the atoms, we have some of them coming out as molecules? The bombardment happens and some of them came out as what? As molecules. They came out as molecules. Then we either have this or this molecule or this molecule. And these molecules we also show on the mass spectrum. You see? Because they will be positively charged because electron is knocked off from the molecules. So what do we see? We may also see these molecules present in the mass spectrum. So sometimes we see instead of these 2 peaks, we see 5 peaks. So the number 2 for Cl35, Cl37, we have seen it. In addition to that, we may see at the end there 70, 72, 74. 70, 72, 74. We have seen this. This is what we are looking for. We have used it to calculate. We are saying sometimes if you have 5 like this and they are telling you it's chlorine in the exam, they may be asking you, yes, you have found chlorine, you have found the isotope, you have found the average, you have been able to calculate the average successfully. What about these 3 guys? What is responsible for them? You say the molecular peaks of chlorine. They are not atomic peaks, they are not isotopic, they are molecular peak because some chlorine did not break. So we have chlorine which did not come out as atom, came out as diatomic molecule. If it is this will give us this 35 plus 35, this gives us 70, and we have 70 peak there. That is the 70 peak. The 70 peak, mass 17. 37 plus 35, 37 plus 37, we have 74. We have 74 peak there. We have peak at 74. Mass 74. Mass 74. And we can also have 35 plus this, making 72. So we have all these masses too. So we have 5 peaks instead of 3 peaks. When this happens, we have both atomic and the molecular there. You know that our element is more than 1 atom diatomic. I hope you understand this. This may come out in the exam. Don't be tricked. Now let's look at the molecular for relative molecular masses. Let's look for that of relative molecular mass spectrum for molecules. So we are looking for relative molecular masses. You can just have it. They will ask you what molecule is this, and you may be given the molecule and they will ask you what these things represent. What these things represent. This is commoner. They will ask you what these peaks represent. For butane, I have it. Butane, you already understand what butane means in your IGCSE. Butane is C for H10, C1, 2, 3, 4, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now this is Butane is an alkane, it's an hydrocarbon, saturated one. Now, when you pass it through the mass spectrometer, this is the spectrum you are getting. Now, for molecule, again, for molecule, we are not making any calculation. We are looking for the molecular peak, not the atomic peak this time around. The molecular peak is always the one farthest to the right. The one farthest to the right. So this one, butane now, the molecular peak here is 58. The molecular mass is 58 for butane. If you see another thing, what is the molecular? Just look at the far right like this. The last one is the molecular mass here. Then, what is the meaning of these three? How come these three? Where are they coming from? Where are these three coming from? Yes, I'll tell you now. You know, during the ionization of these molecules, the molecules came out, then bombardment. During the bombardment, ionization, they came out during the vaporization, came out to the bombardment chamber, electrons bombarded it. From hitting the cathode, electron came out to bombard these molecules. The molecule we are looking for is the one that electron will just be knocked, one electron will be knocked off and it will move. However, this electron may be energetic enough to break the bonds, to break these bonds, to break these bonds. For your information, in organic chemistry, the bonds that are easily broken like this are carbon-carbon, carbon-oxygen, carbon-nitrogen. They easily break. They easily break. Not that other bonds don't get broken, mind you, but these three, they are susceptible to breakage. So, if this one, the peak, the major peak we are looking for is this plus. But if the other three we see there is due to the breaking of these bonds. The breaking of these bonds. What are the possibilities? First, if we break it here, if we break this bond right at the middle, it has divided this compound into two. One is C, H, 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 H. The other one is C, H, now the bond connecting them has been divided. Every bond in organic chemistry, every covalent bond contains 2 electrons. Every covalent bond contains 2 electrons. Now, what happens? When an electron is knocked off from this bond, one electron goes out. So you have one more electron. When an electron is knocked off from this bond, it breaks the bond, but one out of the 2 electrons goes away. One remains. If it remains with this becomes what we call free radical. Free. And this then lacks an electron. It becomes positively charged. Again, if it remains, if it breaks here, one of the electron goes away with the breaking, goes away with the breaking, goes out with the breaking, because one bond is made up of 2 electrons, and the other electron remains as a what? Remains with one of these. If it remains with this, the one it remains with becomes highly energetic, which we will talk about later in your organic chemistry when we are talking about mechanism of organic chemistry reaction or types of organic chemistry reaction, we're going to be talking about this. Free radical. So it becomes a free radical. The electron stays with us as a dot like that. So we say we have C2H5 with the dot. And on this side, the one which now lacks electron, because the bond contains 2 and one is staying with this one went out. So this one will lack electron. It is C2H5 we have plus. It has its own plus. Free radical cannot go into, cannot continue the journey in the spectrometer. Cannot continue the journey because this place is negatively charged. It is going to pull only the positive. Only the positive. So which one is positive? The other one is positive. That is what will continue the journey. So that's why we say one is lost. This becomes lost. The free radical is lost. Again, your free radical is lost. I hope you are jotting this down. All these things I'm doing, I hope you are jotting them down. You are in grade 12. You are doing A levels. Not all the notes you will get. You need to jot some things down. Free radical, one of them, and it is lost. Again, the free radical is lost. So it doesn't continue because it's not positively charged. The one that is positively charged will be dragged by the negatively charged electric field, will be accelerated. This continues the journey. And what is the mass of this? 1, 2, 12 plus 12. This is C2, which is 12 times 2, plus H5, which is 1 times 5, and gives us 24 plus 5. This gives us 29. That is why we have a peak at 29. A peak at 29. A mass that is 29. That is what is responsible for this. C2H5 plus. C2H5 plus. That's one possibility. Don't forget, this is our full C4H10 plus. That's our main molecule. So this is a fragment. Now, we are saying, what if it does not break at the center there? What if it breaks here or here? It means the same thing. Again, I need to clean this now. We finish with that. You know how we got that. So, now, what if it breaks here? What if the breakage is here or here? If it breaks here, of course, as usual, one electron goes. One electron goes. And this bond contains 2 electrons. If one of the electrons comes to this, we have the free radical will be there. C, H, 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 and this one will be C, H, 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 and plus, because it has nothing. One electron is gone, one is with that. So this will be the free radical, and this will continue. That's a possibility. And what is this? 1, 2, 3. C, 3, H, 1, 2, 3, 4, 5, 6, 7, H7. So C3 is, oh, did I say 12 multiplied by 3 plus 1 multiplied by 7. We're looking for the molecular mass of that. So 36 plus 7, this gives us 43. This is responsible for the mass at the peak, which is 43. We have 43 mass here. What is responsible for it? C3H7 plus. So that is what is responsible for that peak. And the other possibility is this. The other possibility is that when this breaks, this one gets the electron, this one gets the electron and becomes free radical, so it's lost, just as this one was lost before. So free radical is always lost. So this becomes lost, and this one has no electron, it becomes positive. So this is what we go through the mass. We continue the journey. So we have this, which is CH3, which is 12 times 1 plus 3 times 1, or 1 times 3. 1 times 3. So this is 12 plus 3, this gives us 15. So in that case, for this possibility, some will also have some that will be this. So that's why 15, we have some at 15. So this is CH3 plus. So these are fragments. The main thing you are looking for is the last one, where no bond is broken, but electron knocked off from one of the atoms. But no bond is broken, but electron knocked off from one of the atoms. So that is what we are looking for. And we are not interested in this, we are interested in this. I hope you understand this. Let's look at another example. For ethanol, I have a peak at 14, I have a peak at 15, I have a peak at 17, I have a peak at 29, I have a peak at 31, I have a peak at 46. Don't mind this small peak, I'm coming back to that tiny peak soon. So 14, 15, 17, 29, 31, and 46. The main peak, which is the molecular peak now for ethanol, is this, at 46. This is our molecular peak, and ethanol is this, which is C2H5OH, which is 12 multiplied by 2 plus 1 multiplied by 5 plus 16 plus 1. This is 24 plus 5, which is 29 plus 17. This gives us 40 what? 1. Okay? When you add everything together, you are going to get 46. Everything gives you 46. So the molecular peak you will get there, 46 is plus. That is the full thing where one electron is knocked off from the atom, from an atom in this molecule, but did not break the bond. No bond was broken, and this is this C2H5OH and our plus. Either you put it here or you put it here, no problem. You have your plus there. That is the mass, the last one. Now these are fragments. And how come this fragment? Where are they from? Let's look at it. There are a lot of possibilities here. This bond will be broken, one electron knocked off, and one electron stays with this. If it stays with this, that's a possibility. We have C. This becomes free radical H, 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 H. So C2H5 free radical, or you put it here, no problem. Free radical will not continue. It's only positive charges that will move. These become OH and plus there. It moves. and it shows it passes through everything where it moves because it is accelerated, it is positively charged. Negatively charged electric field accelerates it in the accelerator, it enters the magnetic field, it is deflected, and it shows at the detector. Then, what is the peak? OH, which is O is 16 plus H is 1. This is 17. So the mass shows at 17. That peak of 17, this 17, we got it, OH plus. That's the second peak, the peak there. That's a fragment. Let's move. If the possibility, there's a possibility that OH, we have the free be the free radical, and this will be our positive charge. So we have C2H5 plus. C2H5 plus. The plus will be here. This will be the one that will move through. That's another possibility. So some of them will happen like this, some of them will happen like that. So what do you have here? C2, that is 12 times 2 plus H5 plus 1 times 5. So this gives us 24 plus 5. This gives us 29. The peak at 29, this is what is responsible for it. C2H5 ion peak. That's a fragment. That's another possibility. And the last two possibilities, let's look at them. If it breaks here, 1, 2, CH3 maybe plus. That means this gives us 12 plus 3 times 1. This is 4. This is 15 peak. Peak at 15. The peak at 15. We have peak at 15. Peak at 15. CH3 plus peak. And what is the other possibility? So we're saying it broke there. Sorry. Peak at 15. And this becomes the free radical. This is CH2OH becomes the free radical. What if this one goes through, this one does not go through? What if the possibility is this? That this one is the free radical and this is the positive ion. So this is the free radical positive ion. We have 12 plus 2 plus 16 plus 1. This 12 plus 2, that is 14. 14 plus 16, that is 14. If it breaks there, 14 plus 16, 30 plus 1, 31. 12 plus 2, 14 plus 16 plus 1. This is 14 plus 16 plus 1. This is 31. We have a peak that is not showing there. It will also show. That will be a peak at 31. A peak at 31. A peak at 31. A peak, oh, it is there. The 31 peak is there. A peak at 31. This is CH2OH plus. And these are the possible peaks. These are the possible peaks. These are the possible peaks. I think we made an error with the 14. Made an error with the 14 there. Oh, sorry. Let's see if we made an error with the 14. Okay, yeah. So these are the peaks you have there. So you have those peaks. You have those peaks. You have those peaks. 1, 2, 3, 4, 4. You have CH3 peak, OH peak, C2H5 peak, C2H5 peak. Let's see very well. Let's look at it again. CH3 peak, we got that. C2H5 peak, we got that. OH peak, we got that. CH this, we got that. So 1, 2, C2, did you get 1, 2, C2H5O, did we get that? C2H5O, did we get that? Let's look at that. C2H5O, C2H5O, in case. Let's look at that. You just have to look at all the possibilities. If it breaks, because this one, OH is like this. What if it breaks here? Let's look at that. If it breaks here, let's look at that. So we have 24 plus 6. 1, 2, 3, 4, 5. 6 plus 6. Plus 16. No? Oh, plus 5 plus 16. That's about 41. About 41. So you look at all the possibility where it can break. Make one the free radical, make the other one the check all the possibilities. I have checked the possibilities. Whatever you are giving, check the possibilities. So I have 15 here. I have OH plus here, which is 17. I have C2H5, which is 29. I have CH2OH, which is 31. CH2OH, which is 31, and I have C2H5OH, which is 40, which is 46, which is 46, which is the main thing. So now that is how to get them. I've given you two examples. Whatever they give you, just go and get it. Now, assuming you have all these peaks, and maybe this was covered for you, and they're asking you to suggest what is here. You know surely that this thing contains CH3. It also contains C2H5. It also contains C2OH. And it has OH. Look at possible combination of these that will give you 46. And OH must be there, because OH, that means it's an alcohol. So look at possible combination with always the OH present that will give you, that if it's this and this, will give you 46. That's ethanol. That is, it shows you. This and this does not give you 46. So it can be that. This and this, there is no alcohol, there is no OH there. This and this also gives you 46. You see what we are talking about? So it is this and this to give you 46, or this and this to give you 46. Then you know what to write here. Then you know it is ethanol. That's another question they can ask you. Again, you know that the thing is 46, but you don't know what is responsible for the 46. But you know the fragments. They give you the fragment. Try join the fragments together and see which combination will give you 46 again. If you join this and this, it will not give you 46. This and this will give you 46. That is one combination. So that means it is ethanol, C2H5OH. This and this will not give you 46, and it does not contain OH. And what you are looking for must contain OH, because there are OH in the fragments. And this also gives you C2H5OH, which is also 46. So that's how you can get, okay, this 46 ethanol is that substance. That can be asked. Now, there is a small peak here. Sometimes it will be more than one. We have what we call M+1 peak. So let's look at M+1 peak, M+2 peak, and M+4 peak. M+1 peak, M+2 peak, M+4 peak. I'm teaching this for your AS. For those of you in grade 12, you may not be asked more than M+1 peak, but you will proceed to grade 13. So it is going to be advantageous for you to listen, so that we get M+1, M+2, M+4. Again, also for some of you, you will be restricted to only the MA at AS. Some of you, we do mass spectrum. We ask to read. You'll be asked to read mass spectrum for atomic, for the atomic mass, relative atomic mass in your Unit 1 exam, and molecular in your Unit 2 exam. And some of you will some exam only have the molecular in AS, level 1 of A level, and atomic in level 1, that's AS, and molecular in level 2. So I'm teaching everything that has to do with it. No knowledge is lost. Get it, and get it now. Even if you don't need it, get it. Just as I always tell you, no knowledge is lost. So M+1 is very important for you, for those of you writing it in AS. But for those of you going to continue it in A2, M+2 is also important. M+4 is also important. What is M+1 peak? There is usually sometimes a small peak here after the molecular peak, the main peak. As a small peak here, that peak is called M+1 peak. M+1 peak. This small peak. This small peak here is M+1 peak. Why +1? Because we calculated everything here. The maximum we have is 46. What if one of the carbon is carbon isotope 13? So that means you have that carbon has a mass of what? 13 instead of 12. We said 12 times 2. So it's not going to be 12 times 2. It's going to be 12 times 1 plus another 13 times 1, because one of the carbon here is isotope 13. Then you added the rest. So 1 has been added to 46 in that case. So what do we have? We now have 47. That is what is M+1 peak. If one of the carbon in this molecule is isotope of what? 13. So we have M+1. This is very common with organic compounds. We have it in organic compounds. Where does M+2 come from then? M+2 peak. That's M+1 peak. M+2 peak. M+2 peak. Imagine you have a compound, an halogenoalkane, an alkane with an halogen attached. I'm going to do this, and I'm going to do this for you. If the halogen attached here, if the chlorine here is chlorine 35, you get your molecular peak. You get your molecular peak at this. This is 12, 13, 14, 15. 15 plus 35 gives you 50. So your peak For that, we'll be at 50. But the chlorine may as well be 37. The chlorine may as well be isotope 37. This is our M. It's our molecular peak. But if it's 37, it will be 12, 13, 14, 15. 15 plus 37, 52. It will be, M here will be 52. That means what we have is M plus 2. This is our M plus 2 now. This is our M plus something. Plus what? Plus 2. In this case, when you have halogenoalkanes like this, and one isotope is 37 and one isotope. How do you know it's chlorine? You will see this peak, 2 peaks. You see this peak and the M plus 1 peak, because this is always 25% 37 and 35 is always 75% isotope. You will see that what you will see that the M and M plus 1 will be ratio of, the abundance will be ratio of 3:1. One will be 75%. The M for the chlorine, the main M for the chlorine will be higher. It will be 3 times this. The one with chlorine 35 will be longer, 3 times of the one that is 25, which is M plus 2. So the M plus 2 will be smaller. So when you see that type of thing, you know that this is chlorine. It is not the same for bromine. For bromine can be bromine 79. When we add everything together, we have 15 plus 79. See, 12, 13, 14, 15 plus 79. This gives us 84. This gives us 94. 94. 94. We get 94. For that, we get 94. Our M will be 94 there. The peak will be at 94. The last peak will be 94. Our M plus 1 plus 2, bromine has another isotope, which is what? 81. 2 more than this. (81). So 94 plus 2, so it becomes M plus 2, which is 94 plus 2, which is, it will appear at 96. That's M plus 2 for this. The difference between this, how do you know it is this or that? Apart from the fact that where they occur, the percentage of bromine 81 to bromine 79 is 50 to 50. So the length of M, the abundance of M and percentage of M plus 2 will be the same. The height will be the same, 50-50. That is M plus 1 and M plus 2. If the isotope, this one is an isotope 81 or 79. If it's 79, it will be M. The M plus 2 will be when this isotope is 81. You see that, just like chlorine. But for chlorine, the M is longer, more abundance than M plus 2. But for this, the 2 of them are the same height. That is another one. What about M plus 4? Again, if you are doing your AS and you are getting confused, stop. You don't have any business with these. Because you get your M and M plus 1, you go away. If you are getting it, flow with us. No knowledge is lost. Get it there before your grade 13. Now let's continue. M plus 4, where does it come from? Sometime I have dichloro Cl, Cl, H, H. This Cl may be 35, 35. This is the M peak. This is the M peak. What if it is not like this? What if it is CH, H, and my Cl, Cl, I have 37, 37. This is a possibility. So this is M for this, and this is M plus 4. Possibility. Die. For this, that will be M plus 4. That's a possibility. Die. 2. So, we are going to stop there. I don't want to confuse you further. For those of you, but before we go, let's look at briefly at the list, this list, the uses of mass spectrometry. What are we finding? We want to know which element or which molecule is present in a particular sample there. For finding environmental toxins, too much, you suspect there is too much toxin in the environment. Grab some air. Is it in the water? Pollution. All those things. Is it in water? Get it. From the water. Water pollution. This is talking about pollution. Get it. From air, from water, from land. Land pollution. Get it. Process, and you can use this to get the substances in there. If the toxin, the pollutant is, you want to know what is responsible, what is in the pollutant, what toxin is causing this sickness or this death. Testing for steroids in athletes. Athletes. When you get the blood or the urine, you want to test the substance there. You want to know if a particular molecule that is banned, that is forbidden for the athlete is there. You use your mass spectrometry. Mass spectrometer to do it. Fighting terrorism. Sometimes some people use biological weapons. Terrorists. In our lab, we have the chemists working on these. They have in the security department. They have sampled different. They have different chemicals they know that can be used to cause terrorism. So, when they suspect anything, they go and test for this very fast. Test for this in the blood of the victim or in the urine of the victim, and they know what is responsible, and they solve this quickly as they counter the terrorism, because they know what is responsible now, what the terrorist is using, and they know how to counter it because they were ready for it. Exploring the universe. Send a probe to Mars to go get some soil sample for you. Send a probe to Uranus to catch some of the atmosphere for you, if there is atmosphere there, or whatever gas you have there. It brings it back to the earth, take it to your lab, use mass spectrometry to get whatever, to know what is there. Drug development and discoveries. This I don't need to explain. You develop drug, you want to know what it contains. You have drug, you develop, you want to know the chemistry of the drug, you want to know the molecular mass of that drug, you use this, or what and what it contains, you use this. Forensics, of course. Somebody has been killed. Was he injected? Inhalation? Poison by mouth, orally? Or how was it done? What is this mark? What is responsible for it? You take sample from the crime scene, take it for forensic. You want to know what molecule or what atom, you can use mass spectrum, mass spectrometry. Geological and archaeological dating. You dig in the ground, the earth, looking for artifacts, looking for archaeological remains of certain things that you want to discover, what has been long lost. Dig, you got something, you are not sure of what it is, you go test. Or you test the bone of people living millions of years back, and you get certain things in the bone, certain things in their remains, and you know that, oh, because they have this in their remains, they must have been hitting that and that and that and that time, or this body is coming from this place because this particular food is more in this area. A lot of things you can use it for. Geology, you are picking stones. You want to know if what a stone is made of. Is it important? Is it very necessary? Is it? Can it be used to make anything? You want to know. For those of you with us during IGCSE when we did radioactivity, when we're trying to calculate the age of rocks, to know the percentage of sodium, potassium, and percentage of lead, percentage of this in a particular, and we use it to calculate the date. You remember from our IGCSE physics, I taught you that. The inorganic dating of rocks. And I also taught you the carbon dating, how to do that. So we need this to get the ratio of the potassium or lead and uranium in the sample of rock. So we need the mass spectrometry. In airport security, somebody is suspected, something is found on him. You want to be sure, because you go to court, you don't want to make mistake. Take this and test. Again, what molecule does it contain? What atoms does it contain? Again, mass spectrometry. These are the uses of mass spectrometry. You may not be asked this, and you may be asked in the exam. So use your head. So we have helped you a great deal here. This is mass spectrometry. This is all those relative atomic mass, relative molecular mass, relative isotopic mass, and this and this and this and this and this and this. You can see what we have been able to come out with mass spectrometry. Student, as usual, send your questions to us. We will reply you within 24 hours with another video custom made for you, as we have promised. You see us again, a video for you, just like you are the only one in the class. And of course, the rule is, the smaller the number of students in the class, the better the learning. Now you are the only one in the class. I am concentrating on you as you are looking at me. I'm teaching you. You alone. And you can ask any question. Nobody's going to laugh at you. Just send your mail and I will reply you. So good day and God bless. Remember, I will reply you with another video within 24 hours.